with audio. Yeah. So let's see just what we have done so far. Okay, we have been talking first to give some general information about the field development process. We talked about the life cycle of the field. Okay. Then we that was last session. It was on Monday. Actually, we covered quite a lot of material. Okay. We first went through the whole process, the way it is structured, the way we call each phase, and what do we have in between these phases to take decisions, and what kind of engineering tasks. Okay, we know also I gave you some idea of what other tasks have to be made. You know, there are many things in the environment, in the political considerations, internal company policy, but these are not the main core of this course. Okay, so just to make you aware of that. And we went through all of it. More or less was a bit boring, but you have to get an idea what kind of engineering tasks have to be made in each phase, and what is the objective. Okay, something that really helps to know or to remember what happens in each phase is to see the objective of each phase. Okay, each phase has a very clear objective, and we are working throughout it just to be able to achieve that objective. Okay. I told you that if you wanted more information, it's a kind of a wealth of information. We have 3 PDOs. One of them is in English, so for most of you that will be appropriate to take a look into the PDO of the Hebron field, and then you can get an idea of the magnitude of work and the kind of things that have to be made. And also some of the things you have learned in other courses, how they fit the PDO. In which phase are you going to be working in the PDO? Okay, or what kind of things are going to be done in the PDO. Okay. So for today we have, let's see, I think it's, we may, have time to do some exercise. But let's see. So today I'm going to talk about more going into one of the topics. We said, I think it was in the first class, what kind of topics we were going to cover. Okay. So more or less we have covered this topic. We are going to have some exercise, and also there will be some discussion today. But basically we are like leaving this topic for now, and we are going into the field production performance. Okay, where we're actually going to make some calculation. Okay, this course is not I will be talking here and you will be listening to what I say, but also you have to learn how to make calculations and make sound engineering analysis. Okay, I think that's the best way to learn. Okay, so the first thing I want to talk today is production modes, okay, or something that is related to production scheduling. So what is production scheduling? Okay, simply is either deciding how much the field will produce in time, right? How will be the rates of oil or gas, okay? But also not only deciding, because I can decide up to a certain point, also predicting, forecasting. Okay, so you have the 2 components. So let's type that here so that we remember production scheduling. So that is deciding or forecasting also rates of, and typically we say we are most interested in the dominant phase, okay, which we call, for example, could be oil or could be gas if it's a gas reservoir, or oil reservoir, oil field, right? But we also want to know, so we decide on these 2, but actually we want to know how the rates of the associated products, okay? Products. If it's a gas field, that will be oil and water. But if it's an oil field, it will be gas and water. And we're going to see now why that's extremely critical. That's very important. I want to know also how these rates and associated products during the life of the field. Okay. And be aware here, I want to highlight these two things. Decide, sometimes I can decide, I can define how much I want to produce, but sometimes simply I just have to forecast. Okay, I have to predict. Okay. So let's talk about production modes. There are two ways in which I can produce a field. Okay, one I call basically two ways to produce a field. Okay. One of them I call production mode A, okay, or we call it also plateau production. Then the other one is called production mode B. Okay. Or also known as decline production. So if you were going to plot with time how the rate of the phase, okay, the rate of the preferred phase, let's say it could be oil or it could be gas, depending what kind of field you have, with time. Okay, this first mode has, of course, it might have some early production that is building up. We will see that a bit later. Okay, might have some early. Just let's neglect that for now. And we have a period where the production is relatively constant, and then at some point it starts to decline. Okay. While in the decline production, like the name states, simply we have a decline from the beginning. Okay. And remember, of course, that's the plan. Usually we put it very nice, very simple, but if you go and actually produce a field in one of these modes, actually probably will be a lot of up and downs, okay? And then also the same thing for the decline. Okay? So that's the real, actually, when I manage to produce the field, and the projected or the calculated probably will be a very smooth line. Okay? Simply, you will see now you have, hopefully we have time today to see, you will get to operate a virtual field, and you will see a bit how difficult it is, okay, to keep on a straight line. Okay, and the same thing for decline. So how do I decide which one to use, plateau production or decline production? Very important. So depending on the product we have, so if it's typically is used, for example, for gas fields, with, and very important, with a contract. Okay. Why? Because I have to ensure the people, depending on this gas, either for heating, either for power generation, they have to make sure that they are getting this gas. Okay, they have a long plan. They want to operate for the next 10 years, 20 years, and they want to make sure they are receiving the gas. Okay, so they have a contract. You're obliged to give some amount of gas. Okay. What else? Yeah, that's not so.
Production facilities, if we can keep
Yeah. So let's put here the word. So it's like big, medium reservoirs. Okay, that's what you are saying before. That is some volume. Okay, that has to be significant enough to, and we'll see that goes to the second part, which is that's usually a standalone development. That requires, that means that it requires its own facilities, offshore structure, okay, etc. Okay, and we are going to go a bit into the economics. I'm going to give some comments, but basically, if, for example, you make a platform, you want it to be producing or to be using those, that will be my capacity, right? I have to build my facility to process this amount of oil and this amount of gas. So if I try to operate like that, that facility, I build it and probably will be used only the first second of the first year of production, okay, which really doesn't make much sense. So really, if I make standalone facilities, offshore structure, I make a big investment, I want it to be operating for a long time at that capacity. Yeah.
But, does it also depend on the type of dry mechanism we are producing with? So
yeah, we go to that a bit. That actually was the article that I told you to read. Okay. So let's wait for that a bit more. Okay. So usually big, medium size. When it's gas, usually if I have a contract, if it's also big, medium size gas field, I operate in plateau rate, and is usually for standalone development. Now, what about this guy? The guy to the right. Okay, if we say, well, the contrast really, it's the philosophy here is to produce as much as possible as early as possible. And we will see now that makes actually a lot of sense from the point of view of the economy, okay? Because every revenue or every oil and gas that we sell later in time, you know, it's going to be discounted. It's going to be worth less. Okay, so I am interested to recover as much as possible as early as possible. But, you know, there are a few things we have to see there. What else? Usually is used for satellite developments. Okay, satellite to either existing fields. Okay, that use existing infrastructure. Okay, like for example, I have one field, Statfjord, or I have an existing field. Okay, and that field has been produced, had to be developed with its own facilities, its own installation, and then at some point it's entering into decline. Okay, initially it was design rate. Okay, for that it was designed for that particular rate, but it has started to decline. Therefore, you have spare capacity here. Okay, at that particular point in time. Okay. Therefore, that particular discovery that you have, okay, which will be your new field, if it's small enough that you can produce it to that existing field, simply you can connect it, and then you can use the spare capacity, and then you can produce as much as possible. Okay, given that you have the capacity to produce like that. Okay. Yeah, so one thing we have to keep in mind, at least for mode A, okay, so let's put it here. There is a relationship between plateau height and plateau duration. Okay, and what is that? What do you think? The longer the plateau? Okay, let's assume the base case, okay, like we had before. What happens if I decide for some reason to produce more? The plateau height to be bigger. Okay, plateau height, I'm referring this guy here. Okay, that's what I say, the plateau height. Okay, smaller what? It should be, yeah, maybe drop fast, I don't know. But the main thing is that it should be shorter, right? Okay, that intuitively you think that if I produce with a higher rate, it will be shorter, and maybe what you said, maybe it drops sharper. Okay, or if I decide to produce with a smaller plateau height, then I will be producing for longer time. Okay, but maybe ask you one thing. So at this time of abandonment, okay, when I reach here, let's say I have defined as my plateau for abandonment or my rate for abandonment, okay, that usually is the rate at which the costs are become equal to the revenue, okay, in which if I keep producing from that point, I will be probably negative. Okay, at that point maybe I decide to abandon the field. Okay, so that's Q, let's call it here Q, abandonment. Okay, so what will be, you think, what will be the produced, the total produced volumes of oil or gas that I have for the three strategies?
Should be same.
Okay, should be the same. So that means the area, okay, that I have under the curve, that's how much I have produced, right? If you say the NP, okay, that's cumulative production. Okay, cumulative production is the integral from 0 to any time t of the rate that I have, either gas or oil, okay, dt. Is counting from the beginning. Okay, so that means it's basically the area under the curve. Okay, so for the first alternative, it will be all of these, right? And if I say until abandonment, okay, until abandonment, how do I call this NP? NPU, right? NP ultimate. That's at abandonment, NPU. Okay, so it's not that I'm trying to recover. Probably I will be able, unless there are some. We will see now that there are some technical constraints. Okay, why I don't want to produce such a high plateau rate. But basically, let's see the area under the curve, under this curve here. Okay, and also under this other curve here. I'm going to make a mess. Okay, should be the same basically. Okay, what I recover in total are usually more or less the same. So that means that this area, let's put it here, okay, is equal to this area, and it's actually equal to this area. Okay. So how do I decide? Let's see how do I decide a bit what plateau, and you're going to have exercise later in the course on that, but how do I decide which plateau height to use? Okay, one of the things, sorry, what's your name? Pita? Alpita. Okay. So one of the things that you mentioned was that you have a contract, right? You have a commitment to deliver some amount of, and that's very typical for gas, okay? So for gas, plateau height, and also length, okay, is given, okay, is given by a contract. Okay, sometimes you can produce more gas if you have, or depending on the length, they want to have contract of 20 years, 10 years, 5 years, and depending on that, you can give more or less gas. Okay, but you have to know really to know well your field. However, for oil, okay, there are some things. So, or also for both, for oil and gas. Okay, one of the things is that usually there is a requirement, at least in Norway, by the authorities to reach certain recovery factor. Okay, so they say, well, at least in the average in the Norwegian continental shelf, I have a recovery factor of so much. You have to aim to reach that recovery factor. So how does the plateau rate affect, why changing the plateau rate can have some effect on recovery factor? Okay, if you look at a very simplistic, assuming we have one well producing more or less, okay, we have water layer and the gas layer, and that well, let's say, is an oil. Okay, if that well is producing in situation 2, let's call this number 2, let's put numbers 1, 2, and 3. Okay, if it's producing in 2, probably will have it will be producing at certain rate. Okay, when you try to produce it at 1, okay, you can do two things. You can increase the number of wells, but that will be expensive. Okay, you're drilling, adding more cost to the field, or you can simply increase the rate of that well. Okay, but you have some physical limit at which you can increase it. Okay, if you increase it too much, you start having coning, right, from the gas layer. You start to have cusping or also coning from the water layer. Okay, you might have also problems with the stability of the formation. You might start to produce too much sand production. Okay, so so usually higher rates can cause, so it's a high GOR, okay, high gas production, high water cut, okay, which is not good for recovery. If you have a channeling between the gas layer and the oil layer, then you are going to leave some oil behind, okay, which is not desirable. You can also cause sand production, okay, and you can also cause, in very extreme cases, a collapse of the near wellbore formation. Okay, so you don't want, if that's a constraint, you don't want, and that can affect your recovery factor. Of course, you want to get more and more. You want to maybe produce in 1, close to 1, without adding more wells, okay, because that's going to increase the cost. So really, okay, so the most robust, or the way it is done to define an economic analysis has to be made. Unless you're bound by contract, right? But always you have to make economic analysis to decide on the plateau rate. Okay? So higher plateau gives you higher revenue, right? Okay. And why is that? Because if that we will see later, but usually we use an equation called, we use an indicator called NPV, which is net present value. Which is, the NPV is the sum of, from year equal 1, that's indicator for year, to the total number of years that you have in the project of the cash flow of that particular year. That CI is the cash flow, and the cash flow is the revenue of that particular year minus the expenses. Okay, divided by, very important, this money, okay, is happening at that particular year. Okay, I am spending on dollars in 10 years from now or 5 years from now, and I'm earning in dollars of 10 years from now. So to be able to sum this money in different times, I use the discount factor, discounting, which is 1 plus some rate, okay, C to the power of I. Okay, and that's what we call the discounting rate, this guy here. Okay, and the discounting rate, it depends on each company, is like an average they have for projects in the same area, okay, compared to if they do something else with the money. Okay, if they go with the money, they will invest in this field and simply put it some other place. They should get better in the field. Okay, they should get a better rate in the field. So that typically is a number between maybe 5. If it's very low, it can go all the way to 15. Okay, but simply it's a number between these two. So if I'm going to use it in the equation, I use 0.05 all the way to 0.15. Okay? Yes?
That's assuming you have a fixed price for over the 10
Yes,
years.
that's the part on the revenue. Well, not exactly. The revenue here will be, so here let's introduce some delta NP or QP. Okay, let's call it QP. Delta QP in that particular year I. So that's the production of, in this case, oil or gas in year I. Okay, and I multiply that by the price of the product, and that can be the price of one particular year, price of that particular product in year I.
So how are we sure that it's more profitable if we produce more in the beginning? What if the price is...
I'm going to that point. Okay, so let's assume that you have, like you said, you have 3 years. Okay, so, or I don't know, some, yeah, I'm making a bit more complicated, but let's see where we end up. Okay, so initially the first years you have some, of course you have, you start getting revenue just, let's say, year when you start production. Okay, so let's say it takes you 5 years to build your field, okay, to build your offshore structure, and then only after year 5 you start production. Yes? Okay, so initially during the first years you'll have expenses, okay, which are, we call, let's call it for now just expenses. Okay, that will be for year, let's say, 1 to 5. I have no revenue. Okay, and then I have to start having for year 1, okay, for year 5. What interest rate do we use for this example? Okay, let's use 0.7. Okay, something in the middle. Here, year 5, and you have some delta QP times the price of year 5. Okay, the price of oil of year 5 minus the expenses of year 5. Okay, these will be expenses related to the operation of the field, so we call it OPEX. of year 5. Okay, plus then we have delta QP of year 6, PO of year 6 minus the OPEX of year 6. Okay, divided by 1 plus 0.07 to the power of 5 at 6, right? And so forth. Yeah, that's I'm decoupling this equation. So that equation told me I have to sum revenue minus expenses. Initially, during the first years when I'm building the field, actually that number will be negative, okay, and it will be very negative. But after, let's say maybe year 5 or 6, depending when I start, let's put here a note, that's when I start production. Okay, and I have the sum. If we are operating the field in plateau rate, okay, this number will be fixed, how much I produce every year, right? And now your question is, what happens if the price, for example, now was $60 and now it goes to 70? Okay, so I tell you to calculate this factor here. The thing is that this factor actually almost always dominates this number, unless that number is extremely, extremely high. Okay, let's say here there was a war, something happened, and the price spiked up to 120. Then it will be what you say, maybe. Maybe it makes more sense to produce more here than here. Okay, but unless you have a big spike, usually if the increase in price is moderate or the decrease in price is moderate, actually this guy will be dominating. Okay. Let's make for a test. Let's make as a test. Let's make a plot of. Okay, let's call this so say year, okay, and then we say 1, 2, 3, and we can make it maybe for 15 years. That field will produce for 15 years, and let's plot that to the power of the year. Okay. Okay, so you see that dramatically starts dropping down. And all, for example, if I'm producing in plateau mode, right? I have the same volumes from here, let's say, to year 10. The revenue that will come from this, from what I produce in year 10, will be half the value of what I get if I produce it in year 1. Okay. And let's say what you were saying, your question, how much the price has to be different from here to compensate by that. Okay? If you have here $60 per barrel, here you will need to have twice, okay, 120. So it will be a big jump simply to justify producing more during at the later stage. Okay? Of course, if you are not magician, but you are, you know, you have your crystal ball and you can see exactly when you have this spike, then you won't be sitting here probably. Okay, you will be making business with Bill Gates or with someone else. Okay, so the point is that the discounting makes sense no matter what the price variation is. It makes sense to produce. So let's put that here. Due to discounting, okay, let me just put that because I think that's very kind of shocking to see this, how they change, and if you use a higher interest rate will be even bigger. Okay, so here we have is 1 over 1 plus c to the power of I. Okay, the discounting factor. We call it sometimes DF. Okay. So what is, besides the technical constraints, the EOR, the coning, what is inhibiting us from producing the highest rate as possible? What is if we are basing our decision on this indicator, this NPV, what is inhibiting from simply produce everything in decline mode? Okay, I don't care. I simply produce what we said here. We have our facilities. We produce as much as possible. Then we make sure this discounting doesn't damage us. Okay, doesn't make too much harm. Okay. We're taking a break soon, so just try to hold tight. Okay, the facilities, right? You see there the expenses. That is something is also affecting the NPV, right? What happens if I have to make a bigger plan? I have to make a bigger platform. Okay, if I have to increase the plateau, the number of wells that I have will be more. Okay, so you have a trade-off. If I increase the plateau rate, this guy will be bigger, simply because I'm producing earlier. I'm recovering that earlier. Okay, especially if I use a constant oil price. Okay. But if I make the plateau higher, then I have to make my facilities bigger simply to take up that rate, to process that rate. Okay? So this will become very negative, this will become very positive, and you have to find simply an equilibrium point where this is maximum. Okay? So these expenses is, let's put it here. So that is wells, that is processing facilities. Okay, that is a platform, and everything has, so it has it is like a rolling ball effect. So if plateau rate is higher, okay, then I probably need bigger processing facilities. I need to have more or bigger separators. I need to have more pumps. I need to have more compressors, bigger processing facilities. Okay, due because I have bigger processing facilities, they are more heavy. Okay, they are heavier. So then I need to have a bigger offshore structure to hold all of this weight. So then I have to big offshore structure. Okay, and also I might need, because of the problem that I mentioned before, you need to have more wells. Okay, therefore this expenses term become very negative. Okay, they start to increase and they become very negative. Also, that affects a bit the OPEX. Okay, it's not the same to have a platform where it's of certain size. You need, for example, 50 people. Then you increase the size. You need maybe 100 people to operate this plant. So that's also affecting your OPEX. Okay, but also revenues become bigger. Okay, because of the discounting. I'm increasing this guy, and then I'm getting, because the discount factor is less, so I'm getting more revenue. Okay, so usually to decide plateau rate, I have to make an economic evaluation. Okay, and that's especially true for oil fields, some gas fields, but usually for oil fields. Okay, but we have some, we will see now, we have, after the break, we have some rules of thumb. Okay, so people start with some, historically they have had many fields, they have producing with some plateau ratio between what I have in place and the height of the plateau, and they use the starting number and then they change it up and down to see if I can get better value. Okay, so that's the way to do it, unless you know some exceptions or an exception. Okay, where we don't want to make more money, it's maybe something could be blending. Okay, you have a crude which is very heavy, and if I simply ship it the way it is, it will have a very low value in the market. Okay, but then I might have a neighboring field which is very nice, very good oil. If I mix these two together, I'm able to sell it at a better price, okay, and faster. So then I want to use a proper ratios to make sure that the product has, you know, exactly the API or the characteristics that I want. Okay, blending. Okay, that is called crude blending of crude.
Is it common to like go for blending of crude from different fields?
In Norway, not so much. I think there are, at least that I know, fields in the UK that use it, and in the Middle East is somehow common.
So like they mix heavy and light crude just like that, or is there any?
You have a blending facility where you mix the two crudes, and at the end, for example, one crude has very low API, one has very high API, one had very high H2S content, the other had low H2S content. You mix them, and you mix them in a ratio that you have a product that is a blend that you can sell at a good price.
So do we mix them before separating or after?
Usually it's after separation, yeah.
After separating.
Depending how close the fields are. But usually the fields might not be very close. Yes?
Because where you know, like most big operators work like different oil fields, like Total, they have so many oil fields. So they normally have like one place where they get all of this crude.
Mm-hmm.
Can combine it or whatever the blending is said.
Mm-hmm.
Sell it after that.
Yeah.
So,
So if you have many fields that's not really, if you can pick from different fields, that's not really a problem, not affecting plateau rate, okay, in a way, because you can get it, if you don't get it from this field, the light oil, you can get it from another field, okay. But maybe sometimes that you have, you cannot get this oil from some other place, okay, so you blend it with an existing field. Okay, let's say that, okay, here you have, okay, you have, if you were going to produce one particular field, let's say a light oil field, okay, you will produce it with a very high plateau, okay, but you have a neighboring field which has very poor API or has some H2S characteristics that you cannot sell it at a good price, okay, so in that case you might decide simply to lower the rate and produce less, okay. But just to make sure you have a good ratio, this number gives you the ratio such that you produce both fields for this time, okay? You produce at the end the same volume or higher volume, but you can sell it at a better price. Or maybe more people, more refineries will accept it, okay? What I'm saying is that if you have many fields, or you can do this mixing that you mentioned, blending in the Bahamas or someplace, okay, you can mix this oil. You don't really have to reduce the plateau rate of this field. You can simply buy oil from some other sources to sell it in the market. Okay. Okay, but let's take a break. Anything else you want to ask? A burning question before we stop? No. Okay. See you in 15 minutes. Okay, so the point I want to make is that we have different ways to produce the field, plateau and decline. If we only look at the revenue, really the decline makes most sense. Okay, we want to produce as much as possible, as early as possible. But you know, we have production mode A, either for gas fields I have a contract, but also the economy simply tells me that I cannot produce in this mode. It's not profitable. Okay, simply because the NPV, or the indicator we use to quantify the economic value of a field, it has two parts. It has the expenses, okay, that depend very much on how much I want to produce, and we have also the revenue. This part will be improved. Actually here revenue is only this part, okay. You have also the operational expenditures, and we have to find an equilibrium, a balance. Okay, simply some people try to maximize that NPV by trying different rates. Okay, remember each iteration might be quite costly, because when you're deciding on the field. By the way, when is this evaluation happening? This plateau height length evaluation. Let's go to our chart that we had here. Okay, where is that happening? Okay, it's in this phase, right? But basically in these two phases. Okay, remember from DG2 everything is more or less locked, so I can make some small variations, but not that many. So really in these phases I have to try different plateau rates, see the length, see how much that affects the economy. And simply it's not that I change and I see immediately the result. Okay, usually remember I have different teams, one of them on facilities, one of them on reservoir. That's the department that actually generates production profiles. So they send it to the guys in facilities, they make the calculation, they send it to the guys in the economy, they make the NPV calculation, and finally that goes to the manager. Okay, now the manager thinks, oh, what happens if we increase the plateau rate? Then you have to tell it to the reservoir guys have to go to the processing guys have to go to economy guys, and finally goes to the manager, maybe 1 month after. Okay, so it's not that we change a number and then we see the variation. Okay, so as part of the complexity of this process, and the industry now is trying to make a platform or like a digital system such that they can change something here and it will propagate through the system and you will see the impact. Okay, it's not so easy because many things require a lot of manual work. Okay, reservoir engineers, they have to be very careful when they set the well conditions, and they have to be very careful when they generate if it makes realistic projection. The guys in processing, they have to size a lot of equipment. Okay, they have to start sizing. If you change the rate, you have to change the separator size. That affects the pump that you need, that affects the compressor that you need, that cascades down. Okay, and then the cost estimation guys, they have to start, okay, now I have a bigger separator, I have to change the thickness, I have to change the power that I need, and then that affects again the economy. So it's all like a chain of events. Okay, in this course we are going to make a simple approximation, all using approximate equations, but it's simply that you see the effect that it has. Okay, so you have to do that yourself, like if you were your own company with all of these departments. Okay, but remember in real life it might take you change something and everybody's going to hate you. Okay, because you
For the oil price, do we take an average based on history matching over the 10 years, for instance, or do we take the current price and we put it as if it's going to be stable?
There are different approaches. Okay, sometimes you use like average for all your assets, sometimes you use the price of the when you plan to start production, sometimes you try to add some variation, but basically it's a static price, and that's something that it's a bit company dependent. Okay, this economic department, they take some assumptions depending on what they think is going to be the projection, and then might take an average, or they might take the price that will be in 5 years from now, they might take the current price, they might take some price from other projects, so it's it really company dependent.
So we will receive the assigned price. If we're planning, we receive it from the...
Well, actually you receive the NPV. If you are a reservoir engineer or are a manager, okay, so you will receive simply the NPV and the assumption, okay. But here in this course, we are going to try to make everything ourselves, okay. So that's why we have to take some approximations of cost, approximations of everything, okay. Yeah. So rule of thumb for first iteration on plateau rate for oil, we typically say we want to produce 10% of NPU per year. Okay? NPU, sometimes I say, remember, this is cumulative, ultimate cumulative production. And this is at abandonment. Okay? That's how much I will produce, which of course there is a lot of uncertainty in this number. Sometimes you may have heard it, not in SPE terminology. SPE terminology, they try to use just one capital letter and everything else should be subscript. Okay. But sometimes you might see also has TRR, which is total recoverable reserves. Okay. So if I have, let's say, so an example, I have a reservoir of 180 million barrels, okay, standard barrels. That's the let's say the N, initial oil in place. Okay, that's okay. Sometimes we use in non-NP-SP nomenclature original oil in place. Okay. So how do we calculate the plateau rate from this number? Okay. We need first to calculate NPU. What is the relationship between NPU and N? RFU, ultimate recovery factor, and to be consistent we have to use subscript times the N, right? That's how much of what I have in place I will be able to recover. Okay, and there is actually quite a big speculation about that number, but you can say from the area, the location, the properties, more or less we know that number will be in a range. Okay, in the North Sea probably will be something between 0.3 and 0.5, okay, for oil. Okay, so you pick a number. What number do we pick here for our N? 0.4, okay. So NPU will be 0.4 of 180. How much is that? 72. Yep. Okay. And now we say we want to produce 10% of that each year in plateau production. Okay. So what else do we need? Plateau rate is NPU times 0.1. Okay, and each company might have a slightly different number. That tells me how much I produce in a year, right? And then I have to divide by the number of days. Plateau rate is usually, the units are standard cubic meter per day or standard barrels per day. Okay, so I have to find the number of days in a year. Okay, but not only that, the number of effective days of production in a year. Okay, I'm not able to produce all days in a year, and that I have what I call the uptime. Okay, so number of producing days in a year. Okay, that it's sometimes the uptime is either simply the number of days I produce in a year, okay, or it's also given as a percentage. I have 80% uptime, 90%, 95%, and that means it's, for example, 95% uptime, that is 0.95 times 365. Okay. And the companies, they have their own records, they have their own, you know, depending on which part of the globe they are, they know more or less, you know, if weather, personnel, all kind of things, they have already some idea what is that number in average. Okay, so let's assume for our case will be 0.9. Okay, and here we have 72 e to the 6 times 0.1. How much is that in barrels per day? You might need Excel. A very advanced calculation. Okay. Okay, so we end up with 20,000 barrels, okay, per day, Plateau. I think so. Okay, which is quite 21,900. Okay, which is actually quite a small reservoir. Okay, so it's a relatively small reservoir. Okay, but that means if you make some assumptions of how much you see the plateau rate of a field, then you make some assumptions, you can more or less estimate how much is in place. Okay, you can try to speculate. If you assume recovery factor, if you assume uptime, if you assume a lot of things, actually you can try to speculate. Okay, the biggest part on speculation is this number, that they use that as a starting point, but then they switch it up and down to maximize NPV. Okay, for gas, that clear? Yep. Okay. For gas, typically, because we want to usually gas with a contract, and you know we want to have it for, we know we don't want to reduce the plateau, but simply we want to be on a contract, so it's typically something between 2 and 5% of, and gas, do we say GPU? Okay, Q is for both phases, either oil or gas. So let's make that comment here. Q is either oil or gas. N is for oil. Okay, and G is for gas. Okay, I guess you covered this before, right? You have seen this nomenclature before. Okay. Okay. Okay, I just want, again, if you have time, you are bored, you know, on a Saturday night, your friends haven't called, or you don't have money to go out, you go and open this file, okay, and you start looking at production profiles of existing fields. Okay, all of the data of Norwegian fields, they are published in the NPD website. Is the Norwegian Petroleum Directorate. Okay, and it has actually a lot of information, a lot of, how many of you have been to this page before? Okay, quite a few. Okay, so you go to, I think it's Facta Sidr. Okay, I should change it in English maybe. Fact pages. Okay, and then you have all kind of information that it's wealth of information, nice to see. Okay, so you have on the wellbore, they are obliged to report information on the wells they drill, licenses, but very interesting for our course, field, producing, and then you can go one by one. Production here. Okay. And they give you for each field, each month, how much they are producing. Okay, all the products they have. NGL, gas, oil, condensate, okay, well, how much water I have produced. So what I have done here in this file, simply took that information, that's the raw data you have. I think this is pre-processed, but I have taken that information and then I made some plots that you can simply change and select the field. Okay. Ormenlange, you see the plateau rate, you see it very clearly. Yeah, is what I told you, right? We make a straight line, we say that's plateau finished, that's actually how it looks like. Okay, because of shutdowns, because of maintenance, because of, you know, simply adjusting the rate, you will see it's quite a big challenge. Okay, and here it seems that it's starting to enter into decline. Okay, we had a plateau production more or less on this section, and then we're starting to go down. And you can select other fields. Let's see, Christine, for example, that's another gas condensate field. Okay. Q gas. So it seems like it had a build up, maybe a short plateau, and then started to decline. Let's say Varosen, that's still producing, no data. This data might not be. Let's see, Hydrun. Okay, Hydrun had some plateau here and then started to go down. Okay, so it's interesting to see, like, I'm going to put first that link on the notes, so when you're bored, okay. And then my Excel sheet, which is kind of okay, so before we go to what you were supposed to read for today, okay, let's see one thing. So why does plateau end? So why okay, why do I have this place that it start to drop production?
Because we don't have enough volume to support, like pressure has declined and now we can't produce at that rate.
Okay, the key word there is you know, energy. Okay, if we want to see it in a way, it's energy. If you have, let's say you have the reservoir, right, and then you have the facilities, okay, that are here. Okay, you have to overcome along the way, you have, and basically that loss in energy we can say is like you have drop in temperature also, but the main thing is the pressure. Okay, here I have some particular pressure, and here I have the separator pressure that I have to reach. Okay, so by the way, how is that separator pressure? Is it constant, changing? If it's constant, why is constant? Changing, why is changing?
Depends on the bottom hole pressure. Either we keep bottom hole pressure constant and produce at varying rate, like changing rate, or depends on also like the friction factor in tube.
Okay, the separator usually, yeah, that's also true, but let's go. So this is only the facilities. Okay, we are not looking at bottom hole at any of the rest of the system. We know we have to deliver at that particular point that has some pressure. Okay, we have to flow against that pressure, and that's the whole thing, that's the whole concept. I have here some pressure, the fluid has some energy, and then has to pay toll, and then has to reach here. Okay, if I try to produce a big volume, this will be bigger. Okay, I have to have more losses along the system. Therefore, if I cannot pay that price with this energy that I have, then I simply have to reduce the rate. I have to produce more, in a very simplistic way. Okay? But here, on the facilities, this pressure is usually kept fixed unless very few cases. Okay, and the way it is kept fixed is, I guess you have seen that before. You have the main separator is called the high pressure separator. Okay, it has a few control measures that are making sure that this pressure is constant. Okay, so you have, if we make it very generic, okay, we have a gas in a very simplistic way, oil. Okay. First you have a level controller. Okay, let's say in a very simplistic way it's a floater. Okay, so then you want to make sure that that level is at a particular height. If it goes too high, what might happen? You might start getting liquid into this line, which is not good. Okay, I have their compressors, I have all kind of things that depend on the phase to be primarily gas. Okay, so this guy is controlling this valve and making sure that the level is within a range. Okay, I have, how do I call these ranges in the separator? Low, high level, and low level. Okay, I think these are, so you have 3 levels in the separator, 4. So low, high level, low level, and this is high, low level, and high level, I think. Okay, so you want to be within the band. If you by any chance start to get too high, then that valve will open. Okay, another control you have, which is important for our case, is this pressure. Okay, I have a pressure gauge, and also the same thing. Okay, if the pressure starts to go up, I open the valve, let more gas go up. The pressure starts to go down, I close it, let less gas go out. Okay, and the reason for that is many of these devices that I have here, they depend on volume, the volumetric rate. Okay, for example, the separator, you need some residence time, right? So you need that the fluid will have, I'm not going a bit into this thing, but I think it's interesting. Okay, if you have the gas, you have some droplets, okay, that they are starting to fall down until they reach the interface and they are part of the oil. Okay, if you circulate them too fast, okay, that means, let's say the pressure went down, volume rate went up, and the velocity is increasing, right? If the velocity of the field, or if the velocity of this droplet of the gas, okay, is higher, then it might not have time to reach the interface, and then it will be dragged with the rest of the fluid. Okay, so in this case, the separator is dependent on, so the operation of the separator is dependent on, first on the Q local. Here we're saying local rate of gas, okay, and liquid, and then it's depending on the velocity of the gas, and then it's depending on the residence time. And that is the same for many other components we have after. We have compressors, we have pumps, we have many things. So if we start changing that pressure, we are affecting the proper operation of everything else downstream. Okay, which process engineers are terrified. Okay, if you go, as you're planning an EOR, let's say, oh, I can get a very nice rate if I lower that pressure. You're going to get screamed, okay, quite a lot. No way, we cannot, no way. Okay, it's actually a big exercise. You have to go and check if now you change that pressure, your volumes will change, and then everything else will change. Yes?
How do you define velocity of gas here? Like what cross-section area do we consider? Because it should be constant, then
you use some the nominal. Okay, so if you see the tank, or the, so it will be, this will be the area of the gas. Okay, so then the velocity of the gas will be the Q of gas at that particular pressure and temperature divided by the cross-section area, okay, which simply will be the area divided by 2. Okay,
the area for gas will be constant. Is it?
yes,
Okay.
you assume that it will be constant. Okay, so if you increase pressure or decrease pressure, this rate will become bigger or smaller. Okay? Yes?
Yeah, so in cases where you have less gas,
In case you have?
where you have less gas and you have
Yeah, so let's say Q. Yeah. Let's take more time on this, okay? Sorry for that. So let's say in the two situations you have the same QG, right? That's standard conditions rate, okay? That is similar to having a mass flow of gas, right? Constant. Yes? If I say constant plateau, 20,000 barrels, okay, or 20 million standard cubic feet if it's gas, okay, is the same as saying that the mass flow is constant, okay? Right? So in one situation, how do you calculate that QG in the separator? You have P separator, okay, a T separator, that will be equal to that mass flow of gas, right, divided by the density of gas at that particular P separator and T separator, right? Okay? So what happens in situation that separator pressure, for example, is 80 bar, okay? 80 bar, you obtain some density, and then you obtain this QG, okay? What happens now when I say is 30 bar separator pressure? Will this density be higher or lower than for 80 bar? Okay, lower, right? So that means that this number will be? Okay, this number is the same for both, right? Let's make one more step, okay? So for P separator equal to 80, right? Let's say that density of the gas is approximately, I don't know, let's say 120, okay? That gives you some QG, right? For P equal 80. Okay. Now for P separator 30 bar, okay, let's say now I have a fantastic idea, I go to my manager and I say, let's reduce the separator pressure, okay? Then I say the density of the gas maybe drops to 60, okay? What will be the relationship between QG at P, this is not standard, okay, this is local rate, okay, P30. Which one will be bigger? Hmm? Okay, will be QG at 30 will be much bigger than the QG at 80. Okay? Right? Because I'm operating still in plateau, so I have the same mg for both. I have the same standard rate for both. Okay? Therefore, what I'm doing, I'm changing density, will be lower for one case, and then this one will be much bigger for that case. And that will affect everything. Residence time, you have to verify that that separator works. Maybe you have to change something in the separator, revamping your facilities. You have to make some investment, and that's not always feasible. Okay? It will be like almost evaluating like almost a new plant. Was a bit clearer now? Yeah? Okay? The thing is that we will see later, to convert these to local conditions, in petroleum we use, remember, petroleum engineers, we are a bit strange, okay? We don't use, if you ask any chemical, mechanical, any other engineer, they will tell you we should produce a field with molar rate, okay? We should produce a field with a mass rate, okay? But petroleum engineers, because they are focused on money, okay? They want to see how much I can sell. So they want to see the money, okay? How many barrels I have to sell, okay? How many standard in volumes, okay? Because that's what I sell. I don't sell moles, I don't sell kilos of gas, I just sell volumes, okay? And then I use this reference pressure called standard cubic meter or standard barrels, okay? But that's equivalent, if I'm operating in plateau, that's equivalent to operating at constant mass flow rate. Okay? Okay. So why does plateau end? So the system energy, let's call it energy, to flow against separator pressure, okay, with the specified plateau rate. Okay, I don't have enough energy to flow against that specified rate. Okay, because we have some losses, we have to flow first from the formation. So we have the fluid goes from reservoir, okay, or it goes to the bottom hole, and then from the bottom hole it goes to the wellhead, and then from the wellhead usually goes to the separator. Okay, and in all of these things we have losses that they are defined by this one we called is a formation, right? Flow in porous media. How do we call that part of the system? That pressure drop, how do we call it? Drawdown, right? Okay. Then we have from bottom hole to wellhead. Here we have it's a pipe, right? It's a pipe pressure loss of the mixture going, and actually I have to cover usually 3,000 meters. It's quite a big change in pressure due to the hydrostatic change. Okay, how do I call that? No, well, I have both, right? So it's simply tubing flow or tubing flow. Then I have from the wellhead to the separator. Here I have again it's same thing, pipe, but it can be a system of pipes. Okay, I have the gathering network. So here I have gathering network. Okay, and I'm losing in each one of them. I'm paying some price until I reach the separator. Okay, so here I have this Q, G or QO that has to go through the whole system. But that's not the whole story. So why can plateau also end? What is another reason that plateau ends? Okay? One thing, I don't have enough energy, and then simply the rate starts to decline. And we will see we have some measures to either add energy to the system or allow it to produce a bit longer. Okay? But what is another reason I have that plateau ends? Okay, these guys that we were mentioning before, that's very correct. Okay, remember I told you forecasting, okay, production scheduling. You say, why do we want these two guys? Okay, why do we care? Maybe the gas we reinject we don't sell. Okay, we cannot use it for revenue. Gas also, the water the same. Why do we take care of the water? Okay. Okay, so let's say that I'm going to call bottlenecking. Which shouldn't happen. Is really the worst thing that can happen when you're in plateau rate. You should want that it's like it dies by itself. Okay, the field is having a great life and then it's simply going down and down and it dies. Okay, that's what you want for the field. But bottlenecking is like suddenly gets like a disease. Okay, suddenly gets something that is going to die early. Okay, so remember when we have the well stream, okay, we come to the first stage. We have separation, okay, and we have stabilization, okay, and after that we get basically three main products. We get and I'm using the wrong colors here, but red should be for gas. Okay, then we get oil, and then we get water. And these guys, they go further to, I have one square saying produce water treatment. I have oil, I have desalting, not done too much in the Norwegian continental shelf, stabilizing. Okay. And then I have in the gas, I have typically dehydration and compression. Okay. I end up with these three products that I might sell, or I might have do for different uses. Okay, so here I have one more step which might be for reinjection, or I also dump it to the ocean, so disposal. Okay. Oil, it goes here to the tanker or to the pipeline, and this gas goes either to the plant or goes again also for reinjection. Okay.
What do we get from stabilization in oil?
Simply the oil that is, you're able to transport it in a tanker on the pipe. Okay. So simply by separation, I mean it's like a multi-stage. That's what typically you have. Is like a multi-stage of separators. Okay. But after that, still the crude has also dehydration. Okay. Has significant amounts of water that you have to remove. Might have salt. You don't want to get corrosion because of water and salt. They can cause corrosion in tanker, in the refinery, many things. And also stabilization, because that oil, if you put it in a tanker, which will be at atmospheric pressure, will still be able to liberate some gas. Okay, so you want to stabilize it and such that it doesn't release that much gas. Okay. Okay. Hope they're not kicking us out, I hope. Okay. So what happens during the life, okay, of the field? So I have, let's say it's an oil field with time, and I have my oil production, gas production. How does it look like? Depending on the recovery strategy, right, that I'm applying to the reservoir. You have seen that if you have, for example, solution gas drive, the gas does, the GOR does something like that. If you have water injection, it does something like that. Okay, it really depends on well, that's not the water rate, but that's okay. So let's assume some mechanism, right? So the water usually increases depending on what kind of aquifer you have, how active it is, but usually you have some increase in water rate, right? Then you reach the plateau, and then it starts to have some sort of decline with the oil. Okay. Okay. The Q of the gas, it has also like a might be constant. Okay, if you are the injection, it's if the injection is keeping it undersaturated, right? If it's keeping it, for example, let's make another simple example. You have an undersaturated reservoir, no gas cap. Okay, and the injection you are having is actually maintaining that pressure. In that case, simply the gas will be constant with the oil. Okay, but you might have other cases where you have a gas cap, and you have the oil, and you have the water, and then by depletion the oil layer is becoming thinner and thinner and thinner, right? And in that case, if it's becoming thinner, you might have starting coning, okay? More coming water into the well. So in that case, the profile actually might look quite a lot like the water. Like you have some increase up to here, and then you start to decline. Okay? So it depends a bit on the... But well, my point is that it's very important to forecast these products. Okay? Why? Try to stay awake for 2 more minutes. We take a break. Okay? Because I have to design these guys. I have to design this guy, this guy, this guy, and this guy. And they depend on these rates. Okay? So if I'm going to design those, and let's say I'm a reservoir engineer, which rates do I give to my processing team? Okay? These rates, right? I have to give them the maximum rates of gas and maximum rates of water that they should be able to process. Okay? Right? Yes?
How did you get water rate, like the plot for water rate?
Well, usually the water cut. Okay. Okay, the water cut with time usually goes up, right? So let's say from 0 can go from 0% all the way to 70, 80%. Okay? So that means, and the water rate, how do we calculate the water rate from the water cut? Okay, water cut divided by 1 minus water cut Q oil, right? I think that's the formula. Okay? Do you know where it comes from? Okay, you have water cut is a Q of water divided by Q liquid total. Okay, Q liquid is Q water plus Q oil, right? And from there you simply clear back calculate Q water, right? So what I'm saying is that when it's constant, okay, and here it's increasing, then you should see an increase in the amount of water, okay, because of this equation. Okay, this one is increasing, so it's going up, 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 until this rate starts to drop, and no matter if this one is going up, still this one is going to go down, okay, because this one dominates usually this part, okay. And the same thing for gas. For gas, actually slightly simpler. Q gas is GOR times Q oil. And the same thing if you say, for example, it's a solution gas oil ratio, solution gas oil drive. Okay, so that's a GOR with time. This guy is actually might be increasing here, okay, but actually this guy is decreasing. Okay. Okay, what were we saying? Okay, so that point that I have, that's why forecasting is so important, okay? Because you have to get this point right, okay? What happens if your actual production, let's say you made your design, okay? So this where your maximum, so this will be your Q water max, and this will be your Q predicted, okay? U gas max, okay? So let's put that comment here. Q gas max and Q water max are used to design the facilities. Okay, so you decide, but what happens now if that's what you projected? Okay, this curve is the projection when you did the planning, okay? But now what happens when you actually start to produce the field, that the rate, let's use another blue, okay? The rate of water actually is like that. Okay? Might be because when we did our initial forecast, okay, let's say we assume that the aquifer was of one particular size, Okay, or we assume one particular vertical permeability. In reality, might be that actually the permeability is much higher, and then the water can reach the well, the production well, faster. Okay, or at an early stage. Okay, we have our and then it can reach. You have channeling. Okay, what happens here in this case? Okay, I cannot. The first thing is you cannot process more than this, right? Your facilities were sized for this rate. You cannot produce more. Then the only solution, this one is increasing more than anticipated. You have to reduce QO. That is something you don't want to happen in your field. Okay.
So it's like we ended the plateau early.
Then you have to start declining here. Okay. Very important, if you have a contract with gas, if this happens, you're in deep trouble. Okay. If you're in oil, you're losing all of this revenue early. Okay. You are starting the decline here. Okay. So you want that prediction to be accurate, and it's one of the biggest uncertainties in field development. Okay. How to capture that behavior in a proper way.
Is it the same for QG max or not?
The same thing. Yeah. Okay. So you can have the same thing that happens here, early.
But how do we predict these QG maximum and QW maximum?
That's your work. Okay? That's your work, the reservoir engineer.
Yeah.
So that's why they are in the project, in the development phase, and then when they go to production, they escape. They go away. Okay?
But like which data do we use without starting production?
No, you have to use a reservoir model that captures that. So you have to run your reservoir model, and you have to have reasonable assumptions of the fault, the permeability, the size of the aquifer, the location of the injector wells. Okay, you have to take all of that into account, because you are the only ones in the process that can give me this plot. Okay, production engineers, we have no idea. Processing manager, nobody knows anything. Okay, so that's why in the book of Dake that I told you to read, he says reservoir engineers, they do the planning, they go away, because if this happens, they are start to find who did this forecast, escaped. Okay, no, went away. Okay, just a joke, but I think it's a kind of help you to remember. Okay, so if QG max, or so not QG max, sorry, if QG or Q water increase quicker than anticipated, okay, then usually the only choice is to reduce QO. Okay, that means declining, enter in decline phase. Okay, that means if I have my Q gas is GOR times Q oil. If this guy is increasing too much, then I have to reduce oil, and Q water. Okay. Also, I have, if this guy is increasing too much, I have to reduce oil rate. Okay. So just, I think before we take a break, okay, sorry that it has taken some time, but I want to show you a case, okay, from Heidrun, from the Norwegian continental shelf. This is a platform. Actually, it's a floating, it's called a TLP. Okay, that is a very amazing. It's a concrete structure which is floating. Okay, and is held by, it has some tethers that they lock it, so it's positively buoyant. If these tethers, they are not in place, it will simply go up. Okay, so they are holding it in place. So let's take these figures. Okay, and here I'm a bit speculating, but that's from the production profile. You can see that that's maybe what happened. Okay, but don't tell Statoil, they might be angry at me. Okay, so this Hydron, okay, is a platform which is floating, and it's a concrete which is very, very, strange to have a concrete structure floating. Then you have some tethers that are holding it to ground. Okay? And the idea is that whenever you have waves or wind or something that moves it out of position, okay, then you have these tethers, if they are ever offset, okay, then you will have a force coming on the tether, okay, that will tend to move it back into place. Okay, it's called a TLP, tension leg platform. Okay, but that's not so interesting with respect to bottlenecking. So I have plotted here rates in colors, okay, water from this from my Excel sheet, oil and gas, and these continuous lines, they are the maximum capacities reported for this field. Okay, so what can you see? What can you see there? You see that you're supposed to have here some plateau, right? If the field was operated in plateau, but then it's starting to go down. Okay, the oil. Now see the water actually is far away from its limit. Okay, but see the gas. Okay, the gas seems that it rocketed up, and then it very quickly reached values close to the capacity. Okay, so what I see is plot, and you see it's actually almost at the same time as I started the decline in the oil phase. So when I see this plot, I can arrive to the conclusion that, because I don't have any other information, I don't work in Equinor, I don't know what happened, but I might say they had a problem with early gas breakthrough. Okay, and that caused that they had to reduce the oil rate because they cannot process more gas. Okay? Alicia, I think it's of course it doesn't look so nice like that plot. Okay, it's not a continuous line, has a lot of up and downs. Okay, but actually it's trying to send you the same message. Okay. Wait. Okay. Yes.
What is the dotted graph that is projected from the oil?
No, that's total liquid. Okay.
Sorry?
Total liquid. Okay.
Yeah.
That's something also something that is important. You see, I think the maximum capacity of liquid is this one. Okay, where you sum the both of them, and that actually has to do with this. With the separator. Okay, that you have. Okay, the separator typically is a three-phase. The first stage is a three-phase, and you have a layer of oil, okay, and a layer of water, okay. So it has, you see, some liquid capacity, the same thing applies here to liquid. You have to have some velocity to allow the gas bubbles, or also the water in the oil and the oil in the water, to separate. Okay, so if you maybe increase this rate too much, okay, you have too much water, for example, then is affecting like the separation of overall of the liquid. Okay, so you have exactly the same issue. If you have the water is like taking space of the oil. And so that's why we have some constraints on the amount of liquid that we process, mainly because of separation. The effect, the water takes space of oil in separation and then causes detrimental separation. Okay. Yeah. Any question before we go for a break? You know, today's a long session, so sorry for that. But the next step is we are going to do some exercise in class, and then we try to finish early. Okay?
There's no question. Because I know like the separator also depends on the waiting time.
Residence time, yeah.
And the residence time of the fluid. So normally, how do you know this?
Well, the
How
T,
do you know, how much time?
the T residence, it's if we calculate it for gas, right, is the volume of gas that you have in the separator. That is this, you know, this area times the length times the, you know, it has this elliptical shape, divided by the Q gas local. Okay, this at separator pressure and T. And this number is usually typically between 3 and 5 minutes. Okay? And also the same thing, you can have a calculated residence time for oil and residence time for gas, for water. Okay? Volume of oil, usually you do it for liquid, divided by QO at that P separator and T separator. Okay? So you have some volume. That's what I told you before. If you have to ensure at least 3 to 5 is optimal to get good separation. Okay? If you do less than that, you might start carrying liquid to the gas and then gas to the liquid. Okay? So to ensure that if this value is too big, then you have to have a bigger volume. Okay? Or you have to have more separators.
3 to 5 minutes, is it for horizontal separators or vertical?
Horizontal. Yeah. I don't remember for vertical. Sorry. Yeah. Yeah. Okay, you need a break? Okay, let's say 15 minutes break, okay? 11:30. Okay, I tried to put some notes in the additional notes on this journal file. So I hope it's understandable, you know, but if not, I will say we have the video. I hope this time it works with the audio. And okay, try to go back if there is something that you don't understand. I just also want to point out that bottlenecking might happen if you have. So first, you could, in principle, if you have, you know, you want to process more water, you want to process more gas, you can simply go and upgrade this package. Okay, so usually it's not that simple. There are some things that are modular that you can simply, if you have space, that's another thing. You can simply add a parallel equipment. You can try to upgrade some equipment, but usually it's very expensive to make these changes. Okay, so really you have to justify, for example, that you will get significant more years of plateau if you do this change. One other thing that might happen, not because these rates increase too much, but because of what you do with that gas. Okay, for example, if you are re-injecting water or gas, there might be some problem with the injector, especially with the injectors of water. Okay, that you start to inject, they might get clogged with time due to oil particles, solid particles, due to bacteria, to all kind of things, and then you cannot dispose of that water. Okay, and then you have, because of that, you have to reduce the oil rate. Okay. Okay, so let's put that comment here. We say that bottlenecking for example, water injectors. Okay, water injector plugging. If that's the case, I can have to evaluate a method to frack. Okay, if I'm afraid of it will break, it will contaminate something, then I don't do fracking, but I probably just re-drill new injector, which is expensive. Sometimes you can have also gas injector collapse or let's say problems. Sometimes you can have bad separation times or higher than anticipated separation times, okay? And that typically happens in, for example, you have the formation of foam. Okay, which is, if you have the liquid, then the gas becomes like a very fine bubbles in a matrix of liquid. Okay, and that is very difficult to separate. And then also you have emulsion. Okay, which is if you have very fine. So this is a fine dispersion of gas in. I guess all of you are familiar with what foam looks like, of gas in liquid. Okay, and it's very difficult to separate, and more common is emulsion, that typically you have, it's a liquid water oil emulsion. Okay, if you try to water an oil, if you mix it very vigorously, for example, if they go through choke, they go through a pump, then there will be a very fine dispersion of, so I'll go with you in a minute. Okay, a very fine dispersion of, okay, water and oil, sorry, this would be dispersion. Okay, we call it fine. These are fine dispersions, that they are, the size is small. Okay, so it takes a long time to separate, and if that happens, then it can bottleneck, because instead of needing 4 minutes, maybe you need 10 minutes to separate, and then your vessel cannot take as much rate as before. Yes?
But can't you mitigate this by injecting maybe before it goes to the separator?
You can inject the emulsifier, you can add some chemicals, you can do something to improve that. Okay, but that is a reason for bottlenecks. Sometimes some oil and water, they resist to any emulsifier or anything, so it's a kind of a, still you need quite a high residence time. Okay, so let's put it here. It can sometimes be mitigated with chemicals. Okay, or with new technology. Okay, or with different technology. Okay. Okay. Now I think there were some things that we had to discuss. First was the differences between onshore and offshore. That I told you to read quite a few pages. Okay, I didn't realize there were so many. Okay, so the first one was onshore versus offshore. That's from the book of Dake, which, if you don't know, is like one of the giants of reservoir engineering, and has quite a few books that are actually a very good reference. So what does it say here about, if you remember, what does it say here about onshore versus offshore?
In onshore we start producing from wells as we will, but in offshore we have to wait until we design production.
That's very true. Okay, so onshore, let's maybe make it here. We usually have, of course, some onshore fields, they behave most like offshore. They are quite remote, they are separated, so you have to build everything from scratch. But some of them, they have neighboring facilities. So you can start, if you're not sure about the size, you make a well and then you start producing for some time, you get some data, and from there you do a better planning. Okay? So you can, it's like, so let's say here, if neighboring facilities are available, it is possible to produce from a few wells, gather more information, okay, and then plan better the field. Okay. While offshore, I usually have nothing. Okay, I have simply the whole sea. So I have to prepare. So I have to. It is necessary to design, construct, and install facilities before producing. Okay, and that's why he discusses that if you compare the profile, this usually has a very quick build-up phase. That's what we call from this period to this period is called the build-up phase. Okay, and then we enter very quickly into plateau. Okay, that's Q. While for onshore, typically we actually can take it a bit more relaxed. Okay, then we make a very smooth build-up, and then we have our plateau, and then we decline. Okay, so longer build up. Okay. So there is here one of the problems I have. I can start in the onshore. I can start earning money early. I can with that finance my operations. Okay, I can have more information, less uncertainty, and I don't have to have such a big expenditure. Offshore, I have to make a lot of expenses initially. So there is a pressure to start producing as much as possible, okay, to start making money. It's like you're spending, nothing is coming into the casa, into the cash, so you have to, so this is, the intention is gain more information about the reservoir. There is also to finance development with these initial wells. Okay. While this one is to there is a push to start production as soon as possible. Okay. You also are making a lot of decisions with big uncertainty. Okay, and also so one of the things are so you want to shorten the build-up phase, and you also want to okay, we want to use here something, we use the pre-drilled wells. Okay, so that means that when we start production, we want to start with as many wells as possible. maybe we need to tie some more wells in the later, but we want to start with a big amount of wells initially, okay, pre-drill wells. While the other gradually is increasing, gradually is building up. You are starting to build your facilities, and finally you can produce the maximum rate. Okay. Any other things that we forgot from Dake?
I have one question. Like when we have, in case of offshore, when we have pre-drilled wells, then why don't we start from the Plateau Production instead of building it slowly?
Yeah, that depends very much on the type of platform you have. So, for example, if it's a subsea field, right? You have a lot of them, and then they go to the FPSO. Okay, very professional drawing. Okay. So in that case, if you are drilling, you go with the drilling ship and you start drilling. For example, you can start production if the FPSO is in place. You can start production from these wells already while the others are being drilled. Okay, but for example, if you have a platform, okay, you have again another very professional drawing. And usually for this type of platforms you have the drilling tower on top. Okay, so you have to be careful if you are producing from one well and you're drilling on the well neighboring it, because remember, we have to move a lot of equipment, BOP, in and out of the well. So we usually don't like to, if one well is producing here, we don't like to avoid causing accidents. You don't want to be drilling on a neighboring well. Okay. So if my development has something like that, like all wells concentrated in one place, that can also happen if I have on a template, we're going to see later, but if I in a template and drilling several wells at the same time, I don't want to produce from them because there is a risk for accident. Okay. But if I have this case that they are quite separate, the vessel has to move significantly from one place to another, I can simply very safely produce from some. And then this one will be like stepwise, while for this case it will be more like a big jump and starting production. Okay. Okay, this will be more like a very steep jump, and this one will be more like a stepwise. Okay. Okay, so see here that also the scheduling is important. When are we drilling wells? If there is any delay, that's going to affect my, and also the facility has to be in place. If there is a delay, that's why so many, yeah, forgot the name in overskridelse. It's overrun, cost overrun. Okay, when you go above the budget. They happen because the offshore processing is not in place yet. Okay. Yes. What else did we have there? That article. Okay. Here is, I think, where they say. Okay. I think it's interesting you read, but I think that's basically the main idea. Okay. They are more costly. You want sometimes if you have big uncertainty, they say you can bring a lightweight platform, small platform. That's actually one idea now is getting a bit popular, that you have a small platform, you actually test how much you have, and then you decide if to have another platform. So make like a stage-wise development. Okay. Okay, so here Dake says that there can be offshore fields that development is resembling those in the offshore environment. Okay. Because simply they are remote, they have no infrastructure. So you have to build everything from scratch. Like they call the field in Yemen, there is a field, Urucu in Brazil is actually in the middle of the forest. So you have to have, you know, the plan, the infrastructure, everything. I think that's... Okay, let's take that part. Okay, so here you have this onshore and offshore. Okay, it tells a bit about what kind of data you have to collect and what kind of things you have to take into account. Okay, that's something interesting he mentions here, that so just to check, who read this document? Don't be embarrassed. No, okay, not many. So please read for next week, okay? I know probably was not a bit short notice, okay? But just read. But he's saying here that, you know, the volumes that you can produce if you do an exploration and appraisal well, actually the drilling ship has very low capacity, okay, of like Separator, to process those rates. So usually these rates are not that high. Okay? If you are in an onshore field and you do an exploration appraisal well, you can change that well later to production, okay, which is a big advantage, and you can produce much higher rates, okay, which gives you a lot more information. Okay? So at the discussion he has here, that offshore, actually these appraisal wells, you get a little bit not too good information because of the capacity of the drilling ship. Remember, if we produce these rates, the drilling ship has to do something with this gas and oil. Okay. Yeah. Okay, so he says very honestly, to be candid, however, at the end of the appraisal phase, irrespective of the technique employed, the quantification of predictions of field performance is anybody's guess, and therefore highly subjective activity. Okay? That's why we have to be able, in all of our workflow, to quantify uncertainty. Okay? So we just don't give a number, but we have to be able to quantify. So for example, if we gave this profile, okay, here, we don't have to be able to provide simply just a number. Okay, but we want to make a range of variation. We think it might be between this maximum and this minimum, and this has the following probability of occurrence. Okay, we think this one will be the most likely. Okay, but I suggest the next part we keep it for Monday. Okay, we have already covered a lot of things, and then the exercise, class exercise, also we do it on Monday. Okay. But please try to read the remaining. Okay, for Monday. Any question before we close? No? Okay, see you on Monday. Have a nice weekend.